Permutation groups are a fundamental concept in abstract algebra, particularly in the study of group theory. They provide a structured framework for analyzing and understanding the symmetries and transformations of mathematical objects. Let's delve into each topic under permutation groups and explore their significance. First, transforming permutations from array form to cycle form and vice versa. Permutations can be represented in two main forms, array form and cycle form. In array form, a permutation is depicted as a sequence of elements shuffled or rearranged. For example, the permutation group of 1, 3, and 2 means that element 1 is mapped to 3 is mapped to 2, and 2 is mapped back to 1. In cycle form, permutations are represented as cycles, where each cycle indicates how elements move within a subset. For instance, the group 1, 3, and 2 represents a cycle where 1 maps to 3, 3 maps to 2, and 2 maps back to 1. To transform permutations from array form to cycle form, we can start by identifying each cycle by tracing the movement of elements. Conversely, to convert from cycle form to array form, we can expand each cycle into its corresponding sequence of elements. Number 2. Expressing permutations as products of disjoint cycles or products of transpositions. Permutations can be expressed as products of disjoint cycles or products of transpositions, which are interchanges of elements. The product of disjoint cycles represents a permutation as a composition of non-intersecting cycles. For example, the group set of 1, 3, and 2, and 4 represents a permutation where 1 maps to 3, 3 maps to 1, 2 maps to 4, and 4 maps to 2. On the other hand, permutations can also be represented as products of transpositions, which are pairwise swaps of elements. For instance, the group set of 1, 2, 1, 3, and 1, 4 represents a permutation where 1 is swapped with 2, then 1 is swapped with 3, and finally 1 is swapped with 4. Number 3. Determining the order, inverse, and product of permutations. Order of a permutation. The order of a permutation is the smallest positive integer k such that raising the permutation to the power of k returns the identity permutation. It can be computed by finding the least common multiple of the cycle lengths. Inverse of a permutation. The inverse of a permutation undoes its effects, resulting in the identity permutation. In cycle notation, the inverse of a cycle is obtained by reversing the direction of each cycle. Product of permutations. The product of two permutations is obtained by composing them, where the second permutation is applied first, followed by the first permutation. In cycle notation, this involves combining the cycles of both permutations into a single permutation. Number 4. Writing solutions and proofs to problems involving permutation groups. Solutions and proofs involving permutation groups often revolve around understanding the properties and behaviors of permutations, such as analyzing the structure of permutations using cycle notation, applying properties like the product of disjoint cycles or the order of permutations to simplify computations. Proving properties such as the commutativity of disjoint cycles or the existence